That's the thing.
Sure, that's a problem indeed.
Fine, sir.
Ma'am,
Ma'am, good morning, ma'am. Our principal ma'am has joined.
good afternoon. Good afternoon.
Good afternoon, ma'am. Yes, ma'am. Sir, shall we start the session? Our principal ma'am has stayed. Ma'am, can we start, ma'am?
Yes, Alamilu.
Yes, ma'am. Please, ma'am. Thank you, ma'am.
Good afternoon, everyone. An equation means nothing to me unless it expresses a thought of God. A quote by SRINIVASA Ramanujan. As a mark of observing National Mathematics Day, we organize international webinar on Ramanujan and continued fraction. A good beginning is halfway done. Let us all begin this occasion by thanking God Almighty by rendering the prayer song.
सत्यव्रतम् सत्यपरम् त्रिसत्यम् सत्यस्य योनिम् निहितम् च सत्ये सत्यस्य सत्यम् हृतसत्यनेत्रम् सत्यात्मकम् त्वाम् शरणम् प्रपन्नाः वाणी गुणानुकतने श्रवणौ कथायाम् हस्तौ च कर्मसु मनस्तव पादयोनः स्मृत्याम् शिरस्तव निवास जगत्प्रणामे दृष्टि सदा दर्शनेषु भवत्तनूना नमो भगवते तस्मै कृष्णायाद्भुतकर्मणे रूपनाम विभेदेन जगत्क्रीडति यो यतः ॐ शान्ति शान्ति शान्तिः.
On this great occasion, I welcome our guest speaker, Professor Benoit Ritard, Associate Professor, Sorbonne Paris Nord University, France. I also welcome our Principal, Dr. R. Geeta Ma'am, Vice Principal, Dr. S. Sita Lakshmi Ma'am, and I extend my welcome to all the faculty members and students. Once again, I welcome you all. Now, I request our Principal, Dr. R. Geeta Ma'am, to share a few words at this juncture.
Good afternoon to all. So we are happy and excited to have with us Dr. Benoit, who is a specialist in combinatorics and number theory, to address all our students. Sir, ours is a women's institution and it is in existence for the past 50 years. And we offer 16 UG courses, 15 PG courses in the self-support stream, and we do have PhD programs in statistics, mathematics, commerce, plant biology and plant biotechnology, then computer science and varied other subjects also. And we do have a good number of students who enroll with us for PhD degree programs. And ours is an institution which is affiliated to University of Madras. To talk in particular about the discipline of mathematics, we offer a UG program, undergraduate program in mathematics and postgraduate program in applicable mathematics. So which is a combination of mathematics and computer science subjects. And students in applicable mathematics, we have a good number of students who are admitted to this particular postgraduate program, and the sort of projects they do, it is also very well acclaimed, and they are able to give solutions for some of the real life problems, both in mathematics as well as in some programs in computer science also. And the curriculum focus is mainly on algebra, mechanics, and then there is differential calculus, integral calculus, trigonometry, operations research, and varied other subjects also. And to bring out the skills amongst the students, they also do programs like problem solving to hone their skills, and for the approach of mathematical problems also. And our college has also started a journal or a book, a research volume called as Sparkles, wherein we invite articles from students to give out their research findings also. And that is also a very good we get good number of articles about that also. Sir, the one thing which we now currently face is that the number of students who enroll for mathematics, previously we would get many applications for mathematics, but to start nowadays what we find is we have students moving into the field of data analytics and statistics, and takers for mathematics. It is not very great, but then we are able to manage it. So I think we would like to get some inputs from you also as to how, apart from the traditional subjects in mathematics, how can we now integrate varied other things? Because combinatorics and number theory is a very important subjects which finds many applications in data analytics and data science, etc. So what best can we do with our curriculum? We would like to have some inputs from you also, sir. How can that be integrated into the curriculum of either your BSc or MSc applicable mathematics, so that we will be able to have this subject as the most sought after subject also. So that is a small thing from my side, and we are really happy to have you here, because getting your overview about mathematics as a discipline from your side, right, from France and Paris, because you would have gone to varied other places also. So getting inputs from you will also help us to make many collaborative programs, or see how we can incorporate some of the changes in our curriculum also. So once again, I thank you very much, and I think I need to thank Dr. Alamelu, who has also made this happen for our students. So an exposure to our students, to people like you, will also help us in their future career also. So thank you so much to all of you. Thank you.
Thank you.
Good afternoon to everyone. Mathematics is the most beautiful and most powerful creation of the human spirit, Stephen Bannon. It is my pleasure to welcome our chief guest, Professor Benoit Rittard, Associate Professor at Sorbonne, Paris, Nord University, France. He is specialized in combinatorics and number theory. He involves history and social impacts of mathematics. He has many presentations and publications. Once again, I warmly and respectfully welcome our chief guest. Welcome you, sir.
Thank you. Thank you for the invitation.
Thank you, sir.
Yes, Professor. Not
Sir?
Priya Bandhavi was not audible.
Shall we start, sir?
Okay. if
Yes,
you want.
yes,
Okay.
yes, we'll start.
Okay, so thank you, everybody. I'm very happy to be here. Not really here, of course, but as I said already last year, it would be so great to meet for real, and hopefully, in the end of the pandemic, we will meet for real, and that will be a great pleasure. It's also a great honor for me to speak to you today, because, especially because of Ramanujan, which is for any mathematician and especially number theorist, a very important man and very particular. And what I would like to talk about today is about a strange problem from Ramanujan and continued fractions, and which is quite interesting to see, to try to understand the way Ramanujan thought. And it's very difficult even for mathematicians to understand the way Ramanujan thought of mathematics, because it was very unusual, very specific, very unique, and probably no other mathematician ever think of mathematics like that in the way he did. So my talk will be about continued fractions, and I will share my if I can. So just give me 1 minute to try and share my well, probably you could do like this. What do you see? So can you see this?
Yes, sir. Yes, sir.
Do you see? Because I cannot see myself, so it's a little bit difficult. So you see what is written here, the Euclidean algorithm?
Yes.
Okay, fine.
Yes, sir.
So this is the beginning of the story when dealing with continued fractions, which was very important for Ramanujan. Starting to study continued fractions implies understanding the Euclidean algorithm. So probably most of you already know exactly what it is about. So if I start with the problem to find the GCD of, say, 30 and 13, then you know how to do this. You apply Euclidean division repeatedly. So first you divide 30 by 13, and this gives you twice 13 plus 4. Then start again with the 13 on 4, which is the remainder of the division. So we get 13 is 3 times 4 plus 1. Then start again with 4 and 1. And 4 is 4 times 1 plus 0. So when we get 0, the last remainder different from 0 is 1, is the answer of the problem. And most of you, I think, know this. And then a more interesting thing for us here is a consequence of this these writings, these equalities. Because consider now the ratio 30 over 13. As written, 30 is 2 times 13 plus 4. So we can write this fraction in this form. And then we have in the numerator and the denominator, we have on both the value 13. So we can simplify a bit the fraction and writing it 2 plus 4 over 13, like this, right? It's just another way of writing the same thing. But now consider the fraction 4 over 13. 4 over 13 is the inverse of 13 over 4. And the reason why I write it this way is that now I can use again what I wrote in the first place for my problem. Write 13 as 3 times 4 plus 1. So I can simplify one more time. And because I have a 4 and a 4, I have two times the value 4, one on the numerator, one on the denominator. If you simplify, you get 3 plus 1 over 4. And again, we could go over and write this way. And this is the end. Now we're done with it. And we have a new way of writing 30 over 13, which is 2 plus 1 over 3 plus 1 over 4. And the values 2, 3, and 4 are said to be the partial quotients of what is said to be a continued fraction. 2 plus 1 over 3 plus 1 over 4 is the continued fraction expansion of 30 over 13. And you understand that this could be done from any fraction. Consider any values, a and b, consider their quotient, then apply the Euclidean algorithm. Then you get the partial quotients simply by considering the quotients of the successive Euclidean divisions you make, right? So you can do it with any, say, rational number or fraction. With two integers. But what's interesting is that in the Euclidean algorithm, in fact, you don't need that the initial values are integers. Here I took 30 and 13, but I could have chosen any other values. The important is the definition of the Euclidean division. If I consider a and b, if I try to consider a over b, then all I have to do is finding the biggest integer q such that q times b is less than a, and then consider the rest r, which may not be an integer if a and b are not themselves integers, but there is no difference in the definition of the Euclidean division, and hence also no difference in the Euclidean algorithm. And this is the real. So you see, I have changed my. You see generalization here.
Yes, sir. We could see.
Yeah, sorry, so I couldn't do a PDF with my files, so it's a little bit. Well, sorry, it's not exactly the way it should have been. So Euclid's original idea was not to find the greatest common divisor between two numbers. His question was a very important theorem, and historically a very crucial theorem in mathematics. His question was, consider the ratio between two numbers, x over y. This ratio is rational if and only if the Euclidean algorithm applied to x and y eventually ends. This is well, it appears in a part of his wonderful book, The Elements, and so for him, what we call the Euclidean algorithm was a way to know whether a number is rational or not. So you may ask, why do I write it this way? Why do I write it x over y, and not just simply x in q? Of course, if it is because you have to consider two numbers to apply the Euclidean algorithm. If you want, you can say y is equal to 1, and that's okay. And well, x belongs to q if and only if the Euclidean algorithm applied to x on 1 eventually ends. To understand this statement, we also have to understand the Euclid standpoint in this. Euclid, what you see here is the original idea from Euclid, but Euclid himself did not write it this way. He did not consider the x over y as a number. The notation were not the same. On his standpoint was very different from ours. And his way of seeing things was purely geometrical. it was not considered in rational numbers as we are, but he was considered in incommensurable length. Two lengths, x and y, are said to be commensurable if and only if we can find a common unit for them. I mean, a length, a smaller length, u, such that x is an integer number, integer times u, and y also an integer times of u. So a unit. We say that u measures x if and only if x is something like n times u, where n is an integer. There are lengths which are commensurable and lengths that are incommensurable, and that's the discovery, one of the main discovery of Greek mathematics in the antiquity. And Euclid knew that very well. He knew the existence of incommensurable lengths, and he stated this theorem to get a kind of general result, to try to find out, to help us find out whether two lengths are commensurable or incommensurable, which is for us equivalent to say that the ratio of the length belongs to the set of rational numbers or not. So this is really a very important thing to understand, is that to know whether a number is rational or not is equivalent to, does an algorithm end or not? And we don't know for sure the way it was applied at the time. So Euclid lived around 300 before the Common Era, and at his time, existence of irrational numbers or incommensurable lengths was known and classical. It was discovered at least a century before. But we don't know for sure the way it was proven. So to prove the theorem here, you see on the screen, is quite, it's okay, it's not that difficult. But to use it, to prove that two given lengths are incommensurable, it's much more difficult, and we don't have a clue of any use of it at Euclidean time. And the first use we know of it goes back to the end of the 19th century by some mathematician not very known today, John Crystal, in a manual for students, undergraduate students, in which he mentions, well, we can do this classical construction. He does not say that the construction is on his own, but he say that, well, geometric constructions for this, to use this theorem is quite classical, but we don't have any clue. It's quite strange. It's quite strange, and it's even stranger at the time of Euclid. This theorem seems to be very important, and nowhere it is used in an explicit way. And it's only in, with Crystal at the end of the 19th century that we have a first explicit use in a geometrical way. And I will not present Crystal's crystal proof, but another one which is really wonderful, to prove that two lengths are incommensurable, that the ratio is irrational. And this proof goes back to 1945, and it has been proposed by Kurt von Fritz in a very nice paper of History of Mathematics. The historical part is not, probably there are some issues in the historical part, but for the mathematical part, it's really wonderful. And here is how it works. So the problem is, you consider a regular pentagon A, B, C, D, E, and I consider also the star, the 5 branch stars made with diagonals AC, CE, EB, BD, and DA. And the question is, prove that the ratio of the diagonal to the side, AC over AB, for example, is irrational in ancient Greek way of doing geometry, we would say prove that AC and AB are incommensurable. They do not have a common unit of length. Of course, nowadays we have many tools to prove it. Probably some of you already did it in some way by complex numbers, by iteration of Pythagorean theorem, or you have many ways to do it. What's interesting is doing it using Euclidean algorithm, Euclid's theorem about rationality linked to the Euclidean algorithm. And does the Euclidean algorithm end? And the proof proposed first so by Kurt von Fritz goes as follows. So consider first the point F, which is the intersection of AC and BD, and write AC over AB as AF plus FC over AB. Okay, it's simple since AF and C are on the same line, and F is between A and C. We can write AC as AF plus FC. This is not difficult. Then we're going to consider the triangle ABF. And our first important step is to prove that this triangle is isosceles in A. That means that AF is equal to AB. And if you look at the fraction in the right, you understand that AF over AB will cancel out. And that will be interesting to get this, that ABF is isosceles. How do we prove that a triangle is isosceles? In general, we consider angles. That is the way we're going to do it to prove it. And we're going to use symmetries in the pentagon in a quite interesting way. So see, in the pentagon, we have these angles beta, which are all equal because of the symmetry of the pentagon. And we also have another kind of angles. We have alpha, which are here, 10 times the angle alpha. All of them are equal, also because of symmetry property. And now consider the triangle ACD. In the triangle ACD, you get 3 times the angle beta and twice the angle alpha. And as you know, in any triangle, the sum of the angles is pi. So here we have 2 alpha plus 3 beta is equal to pi. Now consider the triangle ABC. Again, the sum of its angles is pi. And now you have 4 times the angle alpha and once the angle beta. So 4 alpha plus 1 beta is pi. So we have 2 equations with the unknown alpha and beta. So it's very easy to calculate, to compute the values of alpha and beta. And you'll find very easily that, in fact, alpha and beta are equal to pi over 5. Oh, so there is a question. How can I do this? So somebody raise up his hand. Maybe you can ask a question if you want. No, that's okay. Sorry, to share my computer screen, I cannot see anything of the Zoom session. So if you have a question, you have to talk. No, that's okay.
If there is a question, we'll ask them to post it in the chat box, sir. You can continue, Professor.
Okay.
Fine.
Okay, so we have proven that alpha is equal to beta and equal to pi over 5. So it's very easy from the 2 previous equations. From this and this, you easily get this. So quite unexpected property of the regular pentagon is that these 3 angles are in fact equal. So why is it important for us? Is because now we can go back to our triangle ABF. And we just proved that the angle in A is pi over 5, and the angle in B is alpha plus beta. That means it is 2 pi over 5. And again, we use that in the triangle ABF, the sum of the angles is pi. So you easily get that the angle is in F is 2 pi over 5. That means that the angles in B and F are equal. Hence, the triangle is indeed isosceles in A. So we have that AB and AF are equal length. So we can, in the right, in the expression in the right here, we can replace AF by AB without changing the ratio AC over AB. And AB over AB can be cancels out and gives 1 plus FC over AB. So if you want to see this in the way we see in general the Euclidean algorithm, we just proved that AC is once AB plus a little remainder FC. Now, the next step, if you remember what we did when we considered the fraction 30 over 13, is to inverse and write FC over AB as 1 over AB over FC. And now AB is bigger than FC, so we're gonna start again the Euclidean algorithm. So what can we do to compute AB over FC? So the first thing is to draw another pentagon here, the smaller pentagon FGHIJ, which is also, of course, a regular pentagon by symmetry properties. And this pentagon is going to be useful for us. First, AB, consider the length AB. AB is equal to AF. We just proved this, right? We proved that the triangle ABF is isosceles in A. So AB is equal to AF. And again, by symmetry considerations, AF is equal to CJ. Just as symmetry, simple symmetry around a straight line. So AB is equal to CJ. And CJ can be written as CF plus FJ. Of course, once again, F is between J and C, and F, G, and J and C are on the same line. So we can write CJ as CF plus FG. So again, if you replace AB by CF plus FG, you get CF over FC some way, and there will be a cancellation. And you can write it this way: 1 plus 1 over 1 plus FJ over FC. So it's simple mathematics. It's very nice. It's very just elementary considerations, and we're able, just by symmetries on nice properties of the pentagon, to find a lot of things and to apply repeatedly the Euclidean algorithm. Now, for Fj over Fc, there is one more step, and that will be the last one. Fc. To find out what FC is, we can consider the triangle CFH. CFH is again isosceles triangle in F. This time it's in F, because it's easy to see that the angle in H is alpha and the angle in C is beta. The angle in C is beta. It's trivial. It's the definition of beta we gave in the first place. And the angle in H is alpha because consider the small pentagon FGHIJ. This is a pentagon, a regular pentagon, and in it we have the diagonal. And HF is the diagonal of the pentagon, and HJ is the side. So HFG is is a triangle similar to ABE, say, for example. So the angle is in H is indeed alpha, and since we know that alpha is equal to beta, the triangle CHF is indeed isosceles in F. So the length FC is equal to the length FH as is written in the right. So I can just replace FC by FH in my expression in the right. Why do I do this? So one more time, Fj over Fh, I write it 1 over Fh over Fj, and now it's finished. Why is it finished? And there is a very important phenomenon here. Why is it finished? Because Fh is the diagonal of the pentagon, the red pentagon in the middle, in the center of the picture. Fh is the diagonal and Fj is the side. So Fh over Fj is equal to AC over Fab. AC is the diagonal, AB is the side. So the length Fh and Fj are smaller than AC over AB, but the ratios are the same. If you're not convinced with it, you can start again. You want to study the ratio Fh over Fj. Start again the reasoning we just made with the big pentagon. You will do it again in the smaller one, in the red one, and you'll get that Fh is one time Fj plus a remainder, and the remainder you will also get the same result at a smaller scale, but the same result, the same properties. So if you continue, if we iterate the Euclidean algorithm, then it will never end. It cannot end. We'll get 1 plus 1 over 1 plus 1 over 1 plus 1 over 1, etc. ad infinitum. So by the Euclid, the theorem given by Euclid, AC over AB is irrational. The Euclidean algorithm does not end, so the ratio is irrational. In Euclid's language, AC and AB are incommensurable. Well, we can rewrite it another way, and some of you probably know that AC over AB, the ratio of the diagonal to the side of a regular pentagon, is the golden ratio. And in a modern form, we would write it 1 plus square root of 5 divided by 2. So this is the golden ratio. And one of the important properties of the golden ratio is that when you write its continued fraction expansion, you get 1 plus 1 over 1 plus 1 over 1 plus 1, etc. And this is indeed the most striking continued fraction expansion you can imagine. It has a lot of properties and which make the golden ratio a very important number in number theory. A lot of strange things or numerology around the golden ratio has been said as well, or about golden ratio in some phenomena, natural phenomena. It's not always very sensible, but in mathematics, it's indeed a very important number. And the reason why is not that, well, it is not very understandable if we define it only by 1 plus square root of 5 over 2, why this one would be more important than any other quadratic number. The explanation is given by its continued fraction expansion. Most of the time, in mathematics and number theory, what's important is how to look at numbers. And if you look this way or this way, you don't see the same properties. And looking with continued fractions is helpful to understand the importance of some numbers. So this is I feel is very nice proof because this proof first is helpful to provide an easy example of continued fraction expansion. So we get, in fact, the proof provides explicitly the continued fraction expansions of the expansion of the ratio AC over AB, and with only elementary considerations with angles on isosceles triangle, etc. It's really elementary. I mean, it's always beautiful to see that elementary mathematics, elementary geometry can sometimes get or provide important tools, and continued fractions easily, naturally derives from these this kind of geometrical considerations. But again, this was not done before at least the end of the 19th century, and more developed in the 20th century. And in the 20th century, many authors, in the second part of the 20th century, many authors, many historians of mathematics began to try and find out other proof like this. So there are many of them. We can draw many geometrical figures and to get some continued fractions expansions of numbers. So this is for the golden ratio, but we can have it also as well for the square root of 2. It's very easy as well. So this is either this one or the square root of 2 proof that is given in general. I like this one, but okay, so the square root of 2 is very nice as well. A little less regular, and but you can do it also with a square root of 3 or many other irrational numbers. The limitation of it is that there is an important theorem in continued fraction theory, is that what's the conclusion here that allows us to say that AC over AB does not belong to Q is that we can prove that the algorithm does not end only because the continued fraction expansion is periodic. The periodicity implies infinity. And so any proof like this one, with you put consider a triangle, a square, something like that, and try and go as we just did to get to guarantee that your algorithm will never end. In general, you have to get some periodicity, and all the time you get a smaller picture which is the same as the bigger one, and then you say, oh, okay, so I start again, so it will never end. So indeed, my ratio is irrational. So theoretically speaking, this can work. This works only for quadratic numbers, which are important numbers in general, and also very, very important in geometry, of course, but thanks to Pythagorean theorem. But all numbers are not quadratic numbers, of course. For example, the cubic root of 2 is not a quadratic number, and the fact is that we don't know nowadays. So here's a question for you all: if you want to get to become famous in mathematics, consider what is the continued fraction expansion of the cubic root of 2. No one knows. It's, of course, you can compute the first partial quotients, the beginning, of course, but not all of them. It never ends, of course, because it's an irrational number, but it's not periodic because it's not a quadratic number. So this is an open question for mathematics today, is find out the continued fraction expansion of cubic root of 2. Or pi. Pi is not the continued fraction expansion of pi is not known, and most of number of common mathematical numbers have a continued fraction expansion that we don't know the rule. There is no way of no explicit way to know all of their partial quotients. So this is this kind of things that was important for Ramanujan, and but not for well, it did not have a geometrical point of view on continued fraction. It was more algebraic and theoretical. This presentation I've just made is a kind of well, old-fashioned one. It's just to be more easy to understand in the first place, because the general theory is quite theoretical. Here I just wanted to show some simple things to make you see to make you learn some things about this object. So this object has to be understood as a new way, another way, an alternative way to write numbers. In general, a number, you write it by it's a decimal expansion. That's the most common way of writing numbers, is considering it as a decimal expansion. When this can even be regarded as a definition of real numbers. Real numbers is just a sequence, an infinite, finite or infinite sequence of digits between 0 and 9, and you write them all, and you put some rules to add them, to multiply them. Okay, you have easy property of them, and you can define real numbers like that by seeing them as finite or infinite sequence of digits. But this is only one way to see them. And of course, you can see them in a different way. As you probably know, we can consider binary numeration system or sexagesimal numeration system. And the only reason for which we consider decimal numeration system is probably that because we have 10 fingers, and the fingers were probably our first computer to make calculations, so it was more practical. And also, well, it was not the only numeration system in use, but its success is also due to medieval Indian mathematicians who set up the way we write numbers nowadays, a very efficient way of writing numbers. And it was spread by Arab scientists, and then came to Europe, and then spread all over the world. But all these numeration system in base 10 or in base 2 or in base whatever is just one way to write numbers. What's important in continued fractions is that it's another way to write numbers. And the important thing in this new way is the partial quotients. For the golden ratio, as we have here in the screen, all the partial quotients are equal to 1, 1, 1, 1, 1. All the time. It's periodic. When I wrote 30 over 13, we had 2, 3, 4. It was the three partial quotients, and the partial quotients are the equivalent of the standard decimal expansions. If you know the partial quotients, you know the number, and conversely, to each number corresponds essentially only one continued fraction expansion. So continued fractions can be seen as another way to write numbers. And it's a very powerful way to do so. Because in base 10 or in base 2, there is some arbitrary choice. Why writing in base 10? Again, it's just because we have 10 fingers, but if you write it in another base, well, you get another writing. So why this one and not this one? You understand the point. With continued fractions, it's much you get much more deeper the number, the properties of the number. For example, the first theorem is Euclide's theorem is there are only finitely many partial quotients if and only if the number is rational. So you can see on the continued fraction expansion an important number theoretic property of the number. It's rational. It's rational or not. Same way, if you get the periodic expansion, then it means that you're a quadratic number. That's very important as well. If you consider the decimal expansion of AC over AB of the golden ratio, you get 1.6180339, etc. No rule at all. You cannot, only from its decimal expansion, understand that this is an important number, but you understand it with the continued fraction expansion, because the Euclidean algorithm is a kind of universal algorithm. The Euclidean division is not rooted in any arbitrary base. You don't have this. You have a very natural algorithm. So continued fraction expansion derives from a very natural algorithm. And this is probably because Ramanujan saw numbers, understood numbers as continued fractions. As I said, most of the people see numbers as digits, infinitely or infinitely many digits. For Ramanujan, a number was a continued fraction. That's very strange. That's very difficult because it's much more theoretical, and we're not used to that. Even mathematicians are not always used to that. And I worked with, I published work about continued fraction. I can tell you that this is not easy to see a number really as a continued fraction. But for Ramanujan, it was perfectly natural. It was the right way to understand numbers, and as it seems, he understood numbers more easily as continued fractions as decimal expansion. So that's really impressive. And a famous application of this was a problem which was asked to him by a friend of him, a student, Mahalanobis. It's Ramanujan's houses. I won't go into details about Ramanujan's houses because time flies, but just to make you see, the most important is not here, will not be here the solution of the problem, but the way Ramanujan saw it. So the problem goes as follows. You consider houses in a street, so numbered 1, 2, 3, etc., until the last one numbered n. And Ramanujan was asked the following problem. There is a house numbered m, which has the following property. If you consider the left side of the street, the houses in the left, and you do the sum of all numbers from 1 to m minus 1, and if you do the same at the right side of the mth house, then the two sums are equal. The only complementary information is that n, the total number of houses, is less than 5,000. The question is, what is m and what is n? That's a problem, well, quite simple in some sense, because what is mostly important is to be able to compute this sum. And probably most of you know how we compute this sum. The sum of the number from 1 to m minus 1 is m minus 1 times m over 2. And the same is the same here. So we can put this in equation quite straightforwardly. It's not very difficult. And also, if you try to solve the problem, maybe you will succeed by elementary arithmetic consideration. What's amazing is that Ramanujan solved this problem with continued fractions. And when I first met this problem, when I learned that Ramanujan solved it by continued fractions, I know quite well continued fractions. It's part of my mathematical specialty. I just said to myself, but how can it be? There's nothing common from this with continued fraction and Euclidean algorithm and what I saw you with the pentagon. What's the link? And the fact that there is a link, indeed a deep link, an important link, and that Ramanujan saw it, prove that the mathematics are really very united, a science which is united. And when you're able, as Ramanujan was, to make a link between two situations so different, from our pentagon to this situation, that proof that there is really something, you really feel that there is something important in mathematics. There is something very powerful, very that can unite very so different things. So how did it work? So I will present it very briefly, and but maybe if you have some questions, we can go deeper in the details. What's strange also is that he solved it in only a few seconds. Don't know how he did that. It's really amazing. So the first, when writing the arithmetic considerations I just made, well, so the sum of the first integers, the sum of the first integers minus so the left side, this sum is the sum of the integers from 1 to m minus 1, so it's m minus 1 times m over 2. This sum can be seen as the sum of all integers from 1 over n minus the sum of the first integers from 1 to m. And so writing the equality, and if you write it on, so do some algebra, some computation, you get this. You will probably have to write it, on a paper. Ramanujan did it all in, well, without anything. And in only a few seconds, he understood that this was the equality. And he said afterwards, when he was asked how he gave the answer, he said, well, I understood straightforwardly that a continued fraction was involved. But my question was, which continued fraction was involved? And indeed, there is here a little subtlety. So it's not that trivial, even when we understand pretty well what continued fractions are. So when we get this, we get that. So first one. So here we have a square. There's a square of a fraction. And in the right side, we have 8 plus 1 over m squared. And the idea is that, well, we don't know for sure the value of m on n, but we can expect that m is quite big, reasonably big, at least, well, 10 or 20. So 1 over m squared is a small number. So 2n plus 1 over n squared is close to 8. So when considering the square roots, we get indeed that 2n plus 1 is equal over m is, roughly speaking, close to the square root of 8. That's an interesting way of writing things, because in general, it's irrational numbers that we would like to approximate by decimal numbers or rational numbers. You probably know the Archimedes approximation of pi. Pi is close to 22 over 7. So we have a tricky number, pi. We approximate it with simple number, 22 over 7. And most of the time we expect that this is the way to do. This is the natural way. Here, Ramanujan did the opposite. He said, well, what I'm looking for is n over m, or 2n plus 1 over n. I will approximate it by a much more difficult number, square root of 8. And this is the right way to do. Why? Because of continued fractions. As I said to you, square root of 8 is a quadratic number, so we can get a periodic continued fraction expansion of it. That's probably what was the question of Ramanujan, is which one to consider. I said that there is only one way to get a continued fraction of a number. It's not exactly true, and there are you can well, there are different kinds of continued fraction close to each other. This is not very different. Each of them is not that different from each other. But here we don't need the exact continued fraction of the square root of 8 we would get from the standard Euclidean algorithm. We have to get another one, this one. Root of 8 is 3 minus. It is the minus here, and here give another kind of continued fraction. This equality between the square root of 8 and 3 minus 1 over 6 minus 1 over 6 minus etc. with 6 all the time is can be very easily proven by a geometrical construction. I left it to you as an exercise. Consider a rectangle triangle of sides. So the small sides are square root of 8 and 1, and so the biggest hypotenuse is 3. And from this picture, with the same kind of reasoning as we did for the pentagon, the regular pentagon, you will get quite easily, quite straightforwardly, you will get this equality. I don't know the way Ramanujan got this equality. We can get it also by algebraic arguments, or maybe he was so familiar with numbers that maybe he already knew that the square root was already knew that the square root of 8 was 3 minus 1 over 6 minus 1 over 6, etc. It was probably one of the numbers he knew perfectly even before the problem. And so what's important is in a continued fraction, usefulness of a continued fraction is that when you forget the end of it, you get approximations, rational approximation of the number. For example, here, consider, you can say the square root of 8 is close to 3. It's not exactly 3, but forget the rest, forget the right part of the fraction. It's a first approximation. If you want a better approximation, then consider approximate the square root of 8 as 3 minus 1/6, and forget the other ones. 3 minus 1/6. 3 minus 1/6, which is a 17/6, will get an approximation of the square root of 8 closer to the square root of 8. And if you want a better one, continue, etc. So at one point, when you consider approximation better and better, you'll get successive rational numbers, numerator and denominator. And at some point, if you're lucky enough, one of them will correspond to what you expect, 2n plus 1 over n. And that's what happened to him. This is quite astonishing, because it could fail. This method could fail, but it did not, probably because Ramanujan was so powerful that he knew the best way to go straight to the point. But at some point, the approximation of the square root of 8 to the right, given by the continued fraction, would be equal by accident, but at some point it's quite natural to expect it to happen, to 2n plus 1 over n. So the numerator of the approximation would give you 2n plus 1, and the denominator would give you the m. And that's what happened. So this is if to explain the full idea, and it would take probably much more time to go into the details, but Ramanujan did it, as I said, in only a few seconds. So he was not really he was not a standard mathematician. He was exceptionally clever, brilliant, and this problem really shows the way he saw numbers. Because anybody who does not see numbers as continued fractions is really not drove to this kind of solution. So this is not, of course, it's not the most important result given by Ramanujan, but it's quite telling about the way he saw mathematics. He did mathematics, he understood mathematics, and also about his ability to make links between very different questions. So thank you for attention. And if you have questions, I will be happy to answer, or more precisely to try to answer. Can you hear me?
Yes, sir.
Mm-hmm.
Yeah. Hello.
So yes, there's somebody who raising his hand. So if you have questions, just ask, or you can write on the chat.
Professor, there's a question from the attendee. So we'll pose the question. Sir? Professor, can you hear me?
Yes.
Yeah, there's a question from the attendees.
Mm-hmm.
So actually, they wanted to share the application where Euclidean algorithm is used. And one more thing. So I'd like to know from you about your work on topics with relation to application and other fields.
Application on?
Other fields related to continued fractions.
Sorry, I didn't get the beginning of a sentence. Could you say it again? Can you hear me?
Yes, sir.
I didn't understood what you said. Sorry, can you repeat?
No. Actually, the participant is requested to share some of the application where Euclidean algorithm is used.
So about applications.
The Euclidean algorithm. Application where the Euclidean algorithm is used.
Well, so it's what's interesting is that when Euclid wrote it in the first place, it was not interested in any way in applications. It was purely theoretical, as Greek mathematicians were mainly interested in mathematics for themselves, and without any intent of applying it for for architects or accountants. It was not their considerations, and still it became something important and very and quite useful, and to understand more deeply that for the development of number theory. So in number theory, you consider Euclidean algorithm as the way to define what is said to be a Euclidean ring, and it is a fundamental algebraic structure. So for example, you get a Euclidean algorithm in the set of polynomials. You can divide polynomials and consider Euclidean algorithm in polynomials, then get the equivalent of continued fractions for rational fractions, and a theory which grows which can apply to very different algebraic objects. So in general, the usefulness of the Euclidean algorithm is to find approximations. And one simple application of the Euclidean algorithm, or more precisely in which it can be useful, is our standard calendar, in which, well, as you know, the length of the year, in the ratio between the length of the year, the duration of the year divided by the duration of the day, is a quite tricky number, which is 365.244, etc. And you have to set up a calendar, Julian calendar and Gregorian calendar, which is ours. You have to get clever approximations of it. And the best way to do, the best mathematical way to do it, is to consider a Euclidean algorithm. And that gives you continued fraction expansion, and you cut the remainder in your continued fraction expansion, and you keep only the beginning of it, and you get a rational approximation. And it is also in this way that I think it's Leonhard Euler, great mathematicians of the 18th century, that understood why the Archimedes ratio 22/7 was so close to pi and was so interesting. It provides you 2 decimals. It's because the beginning of the continued fraction expansion of pi gives exactly this the 22/7 when you cut the continued fraction. So anytime you need approximations, you can use continued fraction. That means you use a Euclidean algorithm. I should have also mentioned that this was also considered in medieval mathematics of India by there was an algorithm which was not exactly the Euclidean algorithm. It was set with the Cakravala. Sorry, I don't know how to pronounce it conveniently. And Cakravala was an algorithm set up by I don't remember the author of it. It was to study the length of the different eras as the yugas. So the Kali yugas. How long is the actual Kali Yuga and the preceding eras. And in Indian medieval cosmogony and the different eras on the past, on the future, and there are things which are very close to continued fraction point of view. You put several small eras into a bigger one, and then several bigger ones, etc. And if you write it mathematically, you're very close to continued fractions. And it was indeed an application of it to in the Indian cosmogony to try to know when the world will come at an end. And it's when you see the writings of these authors, we're so close to continued fractions. It's you get the partial quotient written one after the other, but only a sequence of number. It's not understood as a fraction, as a continued fraction, but it's so close. And this, the real writing of continued fraction will have to wait till the Renaissance in Italy. But it's so for more concrete usefulness of it, nowadays we have a consideration of numerical, looking for the Indian English word for this, imagery, when picture on a screen on a computer, how to do well animations, and for this several times you have to make approximations. For example, you have to approximate a curve by a straight line to be able to make computations. And what is the best straight line? And in some cases, it's in many cases you have to make approximation of the slope, and the approximation of a slope typically will involve continued fractions and generalizations, so Stern-Brokow algorithm, etc., and Sturm sequences, etc. So generalizations. So this is a kind of, each time you have approximation of the, arithmetic approximations, and this is very important now today for just your screen. When you draw a line on your screen, you have in general to make approximation, which do I have to put this pixel on or off? This question is solved by mathematics involving the Euclidean algorithm. So
Thank you, sir.
Just a second. I'll be back in just a second.
Okay, sir.
Sorry. So yes, are there other questions?
One more question is there, sir. I'm Angel. So I pose the question. Other than regular pentagon, can you relate any other geometric structure to golden ratio?
So no, the golden ratio is typically the number which will appear, as well as derived numbers, for the geometry of the pentagon. The regular pentagon involves golden ratio. So whenever you get a golden pentagon, you can find golden ratios in many ways. And but if you consider squares, the geometry of the square, then the involved number will be the square root of 2. And if you consider equiangular triangles, then the involved number will be the square root of 3. And for other geometrical figures, you'll get other numbers, but these 3 are the most important, the most common, say. Okay, so golden ratio is important mainly because of its continued fraction expansion. So it's more arithmetic and algebraic properties of it. And while in geometry, it's important as well, because of course the regular pentagon can be seen in many places, and there are also you can find it as well in some triangles. There are also constructions in which the golden ratio is involved. There are a lot of mathematical properties for the golden ratio. What's important with it is to keep it in the mathematical framework, and to avoid seeing it as the key for the universe. There are some possible application in biology, indeed, mainly because it is also related to the Fibonacci sequence, and most properties of the golden ratio is in fact a consequence, can be seen as a consequence of the properties of the Fibonacci sequence. So anytime you see the golden ratio, you can suspect that the Fibonacci sequence is somewhere in the place. And indeed, the Fibonacci sequence can be useful to describe some natural phenomenon. So so you can get the golden ratio as well. But in general, a lot of things has been said about it, and a lot of them were just plain wrong. So what's right is that, what is surely right is that it's a number, it's a fundamental constant of mathematics, as well as pi or e or the square root of 2, say. Are there other questions?
No, sir. Over.
Thank you, sir, for your brief talk about Euclidean algorithm and its generalization. Now, I request attendees to share a few words. Next. Thank you. I request
Happy National Mathematics Day to honorable present here. And Professor, we are confident that the concept about continued fractions using Euclidean algorithm and how continued fractions derive from geometry and involved in Ramanujan's houses you have given are sure to trigger the young minds and motivate them to take up deeper study and analysis and come up with newer concepts and solutions that will contribute to the mathematical world. Thank you very much, sir.
Thank you.
Thank you, ma'am. I request Mrs. K. Priya Banthavi, ma'am, to propose the vote of thanks.
Good evening to all. I deem it's a great honor and privilege to propose the vote of thanks on this memorable occasion. First and foremost, I thank our special guest, Professor Benoit Retard. Sir, thank you very much for your session, who despite his busy schedule has found to grace this occasion. And I also express my heartfelt thanks to our principal, Dr. R. To Dr. R. Geeta ma'am. And further, we are grateful to our head of the department for their words of encouragement, and their guidance has always encouraged us. And also, I thank my colleagues for their kind cooperation in making this function a resounding success. Last but not the least, I thank my dear students for their support to celebrate the National Mathematics Day. Once again, I thank you all for your attention. Thank you, sir. Thank you, ma'am. All.
Thank you for the wonderful session, sir. Thank you so much.
Thank you, Professor. So
Thank you.
sincere and special thanks to you. In spite of your busy schedule, you have agreed to speak to us. Thank you so much, sir. Okay, it's really a very great, and this will benefit for the students to take up further studies. Thank you so much, sir.
Thank you, sir.
So it was a great pleasure for me as well.
Okay.
Hopefully I hope that we'll meet next year for National Mathematical Day.
Yeah, sure, sir.
Definitely.
We'll do advance. Actually, we request you in advance to come and address students in person. Thank you so much, sir.
Thank you.
Bye-bye, sir.
Goodbye.
Thank you, sir.
Goodbye all.
Good. Take care.